Hello everyone. Hope you are doing very well. So today we are going to see the theory part 3 of our chapter alcohols, phenols and ethers. So let's begin today's topic NCRT chapter 7 alcohol, phenols and ethers theory part 3rd NCRT section. So today we are going to specifically cover the section 7.3. This is disclaimer. Objective of today's lecture. After attending this lecture, you will be able to understand the structure, bond length, and bond angle for alcohols, phenols, and ethers. The topics to be covered today, according to the NCRT, first of all, the section 7.3 structures of functional groups. Then we will solve an exercise question 7.2 and then exemplar question number 2 and 12. So let's start with our first topic, that is section 7.3 structures of functional groups, in which let's see and let's talk about the structure and bonding of an alcohol. So let's first of all talk about the methanol, whose formula is CH3OH, and it is the simplest and one of the most common alcohols. Single carbon containing alcohol, the simplest and the most common alcohol is methanol. If we look at the structure and the bonding in ethanol, if we talk about the structure and bonding in methanol, so this is a figure given, figure 7.1, the structure of methanol. You can see that CH3 is bonding with this hydroxyl group OH in a particular manner, and there is this bond angle given of COH. So COH bond angle is given as 108.9 degrees, and there is this bond length given in picometer. The CO bond length is 142 picometers and OH bond length is 96 picometers. So if we talk about the hybridization, the oxygen atom here in the methanol is sp3 hybridized. Okay, that means it is containing 4 hybridized, or you can say 4 hybrid orbitals. If we talk about the bond angle, okay, so hybridization is sp3 for oxygen, and it is the hybridization is important for kind of the structure and the reactivity of a molecule. If we talk about the bond angle in the methanol, the bond angle, COH bond angle is 108.9 degrees, right? So this is the bond angle of COH in the methanol, and this bond angle is slightly less than the ideal tetrahedral bond angle, which is 109.5 degrees. Okay, so hybridization of oxygen atom is sp3, and as per the hybridization, the structure should be tetrahedral, right? But the bond angle of COH, which is 108.9 degree, is slightly lesser than the ideal tetrahedral angle, which is 109.5 degree, right? So 108.9 degrees lesser than 109.5 degrees. Why is it so? So the reason behind this slight decrease in the bond angle in the methanol is lone pair repulsion at the oxygen atom. So the oxygen atom, we have 2 lone pairs present at oxygen atom, and there is lone pair repulsion between these 2 lone pairs. So lone pair repulsion is greater than the bond pair repulsion, and this is the reason which cause a slight lesser bond angle of COH comparatively to ideal tetrahedral angle, which is 109.5 degrees. Now if we move to the bond lengths, we have given 2 bond lengths. So the CO bond length is given as 142 picometers and the OH bond length is given as 96 picometers. You can see there is difference, right? So this is clearly saying us that the CO bond length is comparatively weaker as the OH bond. Okay, so CO bond is comparatively weaker than OH bond, or you can say alternatively that OH bond is stronger than the CO bond as per the given information about the bond lengths. Now, if we see the structure of phenol, so we just have seen the structure of an alcohol, which is methanol. We have talked about the bond angle, the bond length, right? Now, if we move to the structure of phenol, phenol have this structure, figure 7.1 given, showing the structure of phenol. This is benzene ring, and this benzene ring is attaching with the hydroxy group, that is OH group. Okay, so and also the bond length is given, which is 136 picometer of CO bond, and the bond angle is given of COH, which is 109 degrees. Okay, so if we talk about the bond angle is COH bond angle is 109 degrees. Okay, and this 109 degree bond angle of COH is because the sp2 hybridization of carbon electronegativity. Okay, so the carbon which is sp2 hybridized, to which the oxygen is attached, is electronegative, which cause this bond angle to be 109 degrees. Again, a slightly lesser than the ideal tetrahedral angle, 109.5 degrees, right? Now, if you move to the bond lengths, so bond length given is the CO bond length, which is 136 picometers, and this bond length of CO is shorter than in the methanol, which was 142 picometers. Okay, what does it mean? It means that if you see, we just have seen the structure of methanol, right? So in the methanol, the bond angle, or you can say bond length, okay, CO bond length was 142 picometers. But here in the phenol, the bond length of CO decreases from 142 to 136 picometers. Why is it so? Why the CO bond length in the phenol is shorter than in methanol? The reason behind this is the partial double bond character due to the resonance shown by the benzene ring. Okay, so bond length of CO is slightly lesser than methanol due to the partial double bond character due to the conjugation of unshared electron of oxygen with the aromatic ring. Okay, and the carbon is also sp2 hybridized, okay, which cause the angle of COH to be 109 degrees. So this is about the phenol structure. Now, if we talk about the structure and bonding of an ether, okay, so we have seen the alcohol structure, its characteristics like bonding and bond length, bond angle and bond length, and then we have seen the phenol structure, bond length and bond angle. Now we will talk about the bonding and the structure of an ether. First of all, let's take the simplest ether, which is methoxymethane with the molecular formula CH3OCH3. Okay, so this is ROR is a general formula or is general representation for an ether, right? R is representation of alkyl group. Okay, and simplest alkyl group is methyl containing only one carbon. So simplest ether will be methoxymethane having the formula CH3OCH3. That means oxygen is bonding with two methyl groups. This is the structure of methoxymethane given, the figure 7.1. Now we will talk about structure and bonding in the methoxymethane particularly. So this is the structure of methoxymethane. We have given CH3OCH3. Okay, the bond angle is given between COC. So bond angle of COC is 111.7 degrees. And there is also the bond length is given of CO bond, which is 141 picometers. Okay, so if we talk about the hybridization in this methoxymethane, the oxygen atom hybridization is sp3. Okay, and sp3 hybridized means it is arranged kind of tetrahedrally. Okay, so oxygen atom in the ether is sp3 hybridized, and the lone pair and the bond pairs present on the oxygen arranged in the tetrahedral manner. Now, if we move to the bond angle, we have given that the COC bond angle is 111.7 degrees. right? Now, if you observe this, this is slightly greater bond angle than the ideal tetrahedral angle, which is 109.5 degrees, right? 109.5 degrees is very less than 111.7 degrees, okay? Or you can say slightly lesser than 111.7 degrees. So why the bond angle of COC is greater, even though the oxygen is sp3 hybridized and it is arranged in the tetrahedral manner? Still, the bond angle is slightly greater than the ideal tetrahedral angle. Okay, so reason behind is the steric repulsion between the two bulky alkyl groups present around the oxygen. Okay, so these bulky alkyl groups, what they did, they repel from each other and make the bond angle a slightly wider. Okay, this is why the bond angle, the COC bond angle, is slightly greater than the ideal tetrahedral angle, which is 109.5 degrees. Okay, so due to the repulsive interaction between the two bulky alkyl groups, the two bulky R groups around the oxygen atom, causing the slightly greater bond angle between COC. Okay, so 111.7 degrees, a slightly greater bond angle than the ideal tetrahedral angle, 109.5 degrees, and this is due to the repulsion between the two bulky steric repulsion between the two bulky alkyl groups around oxygen. Now, if you move to the bond length given for CO bond is 141 picometers. Now, if you remember, in the methanol, the bond length of CO bond is 142 picometers, right? So, the bond length of CO bond in the ethers is similar to the methanol bond length of CO bond. Okay. Now, let's see the comparison of CO bond length in phenol and ethanol. Okay, so if we talk about the bond length comparison of CO bond in phenol and ethanol respectively, how you can compare them. So first of all, let's take the CO bond length in ethanol. We have seen and we know that the bond length in the CO, like in the CO bond length in the ethanol is 1.42 angstroms. Okay, and the CO bond length in the phenol is 1.36 angstroms. Okay, angstroms is actually 10 to the power minus 10. Okay, so CO bond length in the ethanol is 1.42 and the CO bond length in the phenol is 1.36 angstrom. Okay, now phenol has shorter CO bond length due to the following reasons. Okay, you can clearly see we have given the ethanol and the phenol CO bond length 1.42 and 1.36 angstrom, and the CO bond length in the phenol is actually smaller than the CO bond length in the ethanol. Why is it so? So it is due to, first of all, the resonance shown in the benzene ring, which strengthens the CO bond. Okay, due to the resonance shown by the benzene ring in the phenol, the CO bond is going to be stronger. Okay, and stronger bond means the bond length will going to be decrease. Okay, because if the bond length is shorter, that means the bond is actually stronger. So the resonance is going to strengthen the CO bond forming between the carbon of benzene ring and the hydroxyl or oxygen of hydroxyl. Okay, so that CO bond is strengthened due to the resonance shown by the benzene ring, which is one of the reason due to the which is one of the reason for the shorter CO bond length in the phenol. Also, there is partial double bond character develops in the CO bond. Okay, so because benzene rings is going to show the resonance. Okay, so benzene rings is going to undergo the resonance, due to which there comes a partial double bond character between the C and O bond. Okay, so this resonance is going to strengthen the CO bond. Resonance shown by the benzene ring is going to strengthen the CO bond by developing a partial double bond character among that. And also there is third factor, that greater electronic delocalization. In the phenol will show greater electron delocalization. So the p orbitals in the phenol undergoing the delocalization, which is kind of you can say contributing in the shorter bond length of or shorter CO bond length of phenol. Okay, so these are the three main factors. The resonance shown by the benzene rings, which is strengthening the CO bond by, showing the partial double or by developing a partial double bond character of CO bond. Also, the p orbitals showing the delocalization in the phenol ring. So there is greater electron delocalization, which is causing the bond to be stronger and the bond length of CO to be slightly lesser than in the ethanol comparatively. Okay. Thus, the phenol has shorter CO bond length than in ethanol. Okay, let's solve an exercise question 7.2. The question is, write the structures of compounds whose IUPAC names are as follows. So we have given 10 different compounds. You have to write the structures of these compounds, and the given names are the IUPAC names of the compounds. First one, 2-methyl-butane 2-ol. Second, 1-phenyl-propane 2-ol. Third, 3,5-diamethylhexane 1,3,5-triaol. Fourth, 2,3-diethyl-phenol. Fifth, 1-ethoxypropane. Sixth, 2-ethoxy-3-methylpentane. Seventh, cyclohexyl-methanol. Eighth, 3-cyclohexyl-pentane 3-ol. Ninth, cyclopent-3-ene-1-ol. And 10th is 4-chloro-3-ethyl-butane 1-ol. So let's see their structures. Let's first of all see the structure of the first compound, 2-methyl-butane 2-ol. To draw the chemical structure from the IUPAC name for a given compound, follow these steps. The first one is identify the parent chain. The parent chain means the chain having the largest number of carbon, or you can say longest carbon chain, or the ring structure is going to be our parent chain. You have to identify that. Second step, locate the functional groups like OH for the alcohols, ROR like bond O bond for ethers. Okay, so first of all, you have to identify the parent chain, then you have to locate the functional groups if present in the compound. Third step is add the substituents in the correct position as per the given IUPAC name along with their positions by numbering. Add the substituents, add the particular substituent and the functional group in their correct position as per the given numbers in the name. Fourth step, fulfill the bonding requirement with the remaining hydrogen atoms. Okay, and the remaining valency of carbon or the bond will be filled or fulfilled with the hydrogen atoms. Now let's discuss the structure based on these guidelines or these steps we just have seen. For our first molecule, the first compound, 2-methyl-butane 2-ol, the 4-carbon straight chain with both hydroxyl and methyl group at the second carbon. Okay, so by this name, you can say that at the second carbon, two substituents are present. First of all, the methyl group, and secondly, the alcohol group, that is OH. Okay, so we draw a structure which is containing, so word root is but. But is we used for the 4-carbon chain. So we draw 4-carbon parent chain. At the second position, we add a substituent as OH and methyl at the second position. And then the remaining valencies will be fulfilled by the hydrogen. Okay, and you got this structure of 2-methyl-butane 2-ol. You can even again check by numbering after numbering the parent chain. Now, let's talk about the other two compounds. So, for the second compound, 1-phenyl-propane 2-ol, 3-carbon straight chain. So, we have word root as prop. Okay, the prefix is 1-phenyl, the word root is prop, the primary suffix is ane, and E is replaced by the secondary suffix 2-ol. Okay, so prop means 3-carbon straight chain. So we have 3-carbon straight chain, and at the second position we have alcohol. That means at second position, at second carbon we have OH attached, and phenyl is attached at first carbon. Phenyl means C6H5 group. It is attached at first carbon. By using this concept, you can draw this diagram, or you can draw the structure of compound 1-phenyl prop 2-ol. So we have phenyl at first carbon, 3-carbon chain, second carbon is attaching with the alcohol group OH. So this is the structure. Now, for the third compound, 3,5-dimethyl hexane 1,3,5-triol, we have dimethyl hexane. Hex means 6 carbon. So we have 6 carbon straight chain with 3 hydroxyl groups, because we have 1,3,5-triol. Okay, so OH group, alcohol group, is attaching at first carbon, third carbon and fifth carbon, and the methyl group is again 2 in number and attaching at third and the fifth carbon respectively. So we draw the structure where we choose a single straight chain, 6 carbon a straight chain, and at the fifth position we have added OH, at the third position we have added OH, and at the first carbon we have added OH, and at the third and fifth position we have added methyl, and the other valencies will be fulfilled by the hydrogen atom, and you will got this structure of 3,5-dimethyl hexane 1,3,5-triol. Now for the fourth compound, 2,3-diethyl phenol, diethyl phenol. Okay, so phenol, which is C6H5OH, will be our like parent chain, you can say. Okay, now 2-ethyl group is present as a substituent on it, that is C2H5 group at the position second carbon and the third carbon. So we have this phenol, and at second carbon we have ethyl, and at the third carbon we have ethyl. Okay, so we got 2,3-diethyl phenol structure. For the fifth compound, 1-ethoxypropane. Propane means the propane 3-carbon chain connected to a ethoxy group, okay, at the first carbon, 1-ethoxy. Okay, ethoxy group means OCH2CH3 group. Now if you remember, we have studied that in the ethers the two R groups may be same, may not be same. Okay, if they are not same, then the longer carbon alkyl group will be considered as the parent chain, and then another will be alkoxy. Okay, so ethoxy is your substituent at the first carbon of propane. So you have this structure, you write the propane chain, and then at first carbon add the ethoxy substituent. So this is the structure for 1-ethoxypropane. For the sixth compound, 2-ethoxy-3-methylpentane, 5-carbon chain with ethoxy, OCH2CH3 group at second carbon and methyl at third carbon. Okay, so we have pentane. Okay, pentane means 5-carbon chain we have, and at the second position we have ethoxy group attached, that is OCH2CH3, and at the third position, third carbon, we have methyl group attached. So we draw the pentane first of all, and then at the second carbon we attached ethoxy substituent and third carbon attached with methyl substituent, and you will get the structure of 2-ethoxy-3-methylpentane. Then comes the seventh compound, cyclohexyl methanol. So we have cyclo. Okay, so cyclohexyl methanol, that means you have a cyclohexane ring as a parent ring with CH2OH, that means methanol group attached at the first carbon, you can say. So you got this structure of cyclohexyl methanol. The first carbon is attaching with CH2OH, the methanol substituent. Then comes the eighth compound, 3-cyclohexyl pentane 3-ol. Now for this, pentane means 5-carbon chain with cyclohexyl present at the third carbon. Cyclohexyl means C6H11. And also the 3-ol. 3-ol means the alcohol group, the OH group, is attached at again the third carbon. So at the third carbon we have cyclohexyl and alcohol group, both are attached, and we have the parent chain as pentane. So we firstly write the pentane chain, and at the third carbon we attach the alcohol and the cyclohexyl, and you got the structure of 3-cyclohexyl pentane 3-ol. Then we have this ninth compound, cyclopent 3-in-1-ol. So again we have pent and cyclo. So we have a cyclopentane ring with double bond at the third position because it is given 3-ene. Okay, ene suffix is for alkenes. Okay, that means double bond carbon. So cyclopentane ring at the third carbon we have you can say alkene attached. Okay, and also alkene attached means at the third carbon we have double bond. Okay, between the carbons we have double bond, and there is OH group, that is alcohol group, at the first position carbon. So we first of all draw the structure of cyclopentane. Then at the third carbon we have the double bond. So between now you can decide that third carbon is attaching with the double bond with another carbon, but it is here with the second or the fourth. Okay, that you have to cover by understanding that at very first carbon we have hydroxyl. So from first to third, if you move 1, 2, 3 and then 4. Okay, so if the double bond is here between 2 and 3, the numbering will come in the name as 2-ene because the lowest number will be there with the double bond carbon, right? But we have given the 3 as a number in the name, then that means that 3 and 4 carbon is included with double bond. Okay, so this is the structure we got for cyclopent 3-in-1-ol. Now for the last part, the 10th compound, which is 4-chloro-3-ethyl butane 1-ol. So we have 4 carbon chain because butane we have given 4 carbon chain, OH group, alcohol group at first carbon, ethyl group C2H5 at third carbon, and chloro group at the fourth carbon. So you draw the butane, the 4 carbon chain, third carbon attaching with the substituent ethyl, fourth carbon attaching with chlorine, and first carbon attaching with hydroxyl, and you got the structure of 4-chloro-3-ethyl butane 1-ol. Okay, now let's see an exemplar, or you can say NCERT exemplar question number 2. Question is, how many alcohols with the molecular formula C4H10O are chiral in the nature? So how many of the alcohols whose molecular formula is given, structurally they can be different. The molecular formula is C4H10O. How many of these alcohols are chiral? So that you have to decide by drawing the different structures having this molecular formula. Okay, the options are 1, 2, 3 or 4. So for this question, the correct answer is option A, that is 1. That means only one alcohol with given molecular formula R is chiral in nature. So what is chiral carbon? First of all, so carbon which is containing 4 different group attaching with it is considered as chiral carbon. And for alcohols are possible for the molecular formula C4H10O. With this molecular formula, 4 different alcohols are possible which are structurally different. So the structural formula of these isomers are given below. First of all is butane 1-ol. Okay, you take a straight chain of carbon, 4 carbon, and attach the hydroxyl group at very first carbon. You get butane 1-ol having molecular formula C4H10O. Then you can also draw this as butane 2-ol. You just change the position of hydroxyl group at the second carbon and got butane 2-ol. Then 2-methyl propane 2-ol. This is also isomer of molecular formula C4H10O, where at the second carbon we have hydroxyl group and methyl group both are attached. And then we got 2-methyl propane 1-ol. That means the hydroxyl is same at the very first carbon, but one of the methyl is substituted at the second carbon. So you got this 4 different isomers having the molecular formula C4H10O. Now from these different 4 isomers, you have to select the alcohol which is chiral in nature, which is containing the carbon which is having 4 different group attached to it. So no chiral center is present in butane 1-ol, 2-methyl propane 1-ol and 2-methyl propane 2-ol. So between first, third and fourth, no chiral center is present in these alcohols. Okay, you can see that in the butane 1-ol, every carbon is attaching with similar two groups of hydrogen, or you can say two similar hydrogen atoms, right? Similarly, in 2-methyl propane 2-ol, not any single carbon is present with 4 different groups. And similarly, in the 2-methyl propane 1-ol, not any carbon is present or bonded with the different 4 groups. So these 3 alcohols are achiral compounds because they doesn't contain any chiral carbon. Only the butane 2-ol contain a chiral center, which we represent by a star. So this carbon having star is actually chiral carbon because it is attaching with one hydrogen atom, CH3 atom, CH3 substituent, OH substituent, and CH2 CH3, that is ethyl group substituent. Okay, so all the different groups are attached with this carbon. So this carbon is chiral, and hence this butane 2-ol alcohol is a chiral alcohol. So this is a chiral compound, and therefore the correct option is the option A, that is only one alcohol with the molecular formula C4H10O is chiral in nature. Now let's solve our next NCERT examiner question number 12. The question is, phenol is less acidic than. So you have to tell from the options that which compound is more acidic, or you can say phenol is less acidic than which of the following compounds. Options are ethanol, orthonitrophenol, orthomethylphenol, or orthomethoxyphenol. So for this question, the correct answer is option B, that is orthonitrophenol. Electron withdrawing groups, which withdraws the electrons from the benzene ring, because we are talking about phenol. Okay, and on the phenol, if any electron withdrawing group is present, which is going to withdraw the electron density towards itself from the benzene ring, the OH bond of the phenol will becomes more polar, right? So electron withdrawing group if present on the phenol, it is going to withdraw the electrons from the benzene ring towards itself, which is going to make the OH bond present in the phenol more polar. That means the charge distribution, the partial charge distribution, delta negative and delta positive between the oxygen and hydrogen becomes more. Okay, acidity is higher than phenol. Okay, and also in the orthonitrophenol, acidity is higher comparatively to phenol because nitro group is attached at the ortho position in the orthonitrophenol. Okay, because it is present at the ortho position, which is actually the second position comparatively to the first position at which the hydroxyl group is attached in the phenol. So at the second position carbon, we have nitro group attached, which is actually electron withdrawing group, which withdraws the electrons density towards itself from the benzene ring, make it unstable, and the OH bond will become polar, more polar comparative to phenol. Phenol doesn't contain any electron withdrawing group, right? That's why acidity in the orthonitrophenol is higher than the phenol, and electron donating group if attached, you can say in the phenol, then it will going to donate the electron to the benzene ring. Okay, benzene ring is already electron rich, and if any electron donating group attached to it, it will donate its electrons towards the benzene ring, and OH bond will become lesser polar. Okay, in that case, what will happen? The acidity of the phenol, or you can say acidity of that electron donating group substituted phenol, will become lower than the phenol, because phenol doesn't contain any electron donating group. But if any electron donating group is present in the phenol structure, then the acidity will become lower comparative to phenol. Ethanol is less acidic than phenol. Okay, ethanol is less acidic than phenol. Why is it so? Because In the phenol, the phenoxide ion is more stable than the ethoxide ion because of the resonance present in the benzene ring, shown by the benzene ring in the phenol. Phenoxide means benzene ring attaching with O negative. The H positive is removed, O negative remains, and that phenoxide ion is going to be more stable comparative to the ethoxide, that is CH3, CH2, O negative. Why is it so? Because there is resonance factor in the benzene ring, shown by the benzene ring in phenol, which is going to stabilize the phenoxide ion. So if you can see, this is the stability order between the phenoxide ion and the ethoxide ion. So the phenoxide ion is more stable than the ethoxide ion, due to which ethanol is less acidic than the phenol, because phenol will lose its H positive and become phenoxide ion, and also it is stable comparative to ethoxide ion. On the other hand, ethoxide ion, when loses its H positive, it is not comparatively stable, right? And resonance factor is stabilizing the phenoxide ion, so stability is more in the case of phenoxide. This is why the ethanol is lesser, or you can say ethanol is lesser acidic than the phenol. So the correct option is option B, that is orthonitrophenol. That means the nitro group is attaching at the ortho positions and you are getting orthonitrophenol. Okay. So phenol, the question was that phenol is less acidic than which one? Okay. Because ethanol is already less acidic than phenol, so ethanol can't be the answer. So your correct answer is actually orthonitrophenol, in which the acidity is more comparatively to phenol. Why? Because nitro group, NO2 group, is electron withdrawing group present at the ortho position, withdrawing the electrons from the benzene ring towards itself, making the OH bond more polar and making it easy to remove the H positive from the phenol ring. Okay, and increasing the acidity comparatively to the phenol. So correct option is option B, that is orthonitrophenol. Okay, let's look at the summary, the points to remember from this lecture. First of all, the alcohols are OH, having the general formula ROH. Phenols, having general formula the benzene ring and OH. And the ethers are OR prime. R and R prime may or may not be same. They all have sp3 hybridized oxygen. Okay, so when they are attaching with the alcohol group, they all like in the alcohol and phenols, and when in the ethers oxygen is present, two alkyl groups are attaching with the oxygen. Their oxygen in all these molecules, alcohol, phenol and ethers, all have sp3 hybridized oxygen. And the COH bond angles vary due to the different factors in the different molecules. And what are these factors? So if we talk about the alcohol particularly, there is lone pair repulsion on the oxygen atom in the alcohol molecule. So alcohols have lone pair repulsion, and the lone pairs is present on the oxygen, due to which the bond angle due to the repulsion between lone pair, which is greater than the bond pair repulsion, the bond angle will decrease or slightly decrease than the ideal tetrahedral bond angle, which is 109.5 degrees. In the phenols, the hybridization of carbon, which is attached with the hydroxyl group, is the main factor, due to which the COH bond angle vary. Okay, so hybridization in the phenol, the hybridization of carbon, which is sp2, which is attaching with the sp3 hybridized oxygen, is the main factor for the very COH bond angle in the phenols. Okay, so if you see, this is alcohol bond angle, or you can say COH or ROH bond angle, which is 108.9 degrees in the alcohol, which is slightly lesser than the ideal tetrahedral bond angle, which is 109.5 degrees. And this is phenol, having 109 degrees bond angle, which is a very slight, you can say, less than the ideal tetrahedral bond angle. Why we are saying tetrahedral? Because oxygen is sp3 hybridized, the arrangement should be tetrahedral. Okay, but due to the sp2 hybridization of this carbon of benzene ring, which is attaching with the sp3 hybridized oxygen, the bond angle is 109 degrees, which is varying. Now, the CO bond length order, if we have seen, the CO bond length in the alcohols is largest. Then comes the ethers, which is similar to the alcohol, and the lowest is possible in phenols. Why? Because in the phenols, there is partial double bond character due to the conjugation of unshared electrons of oxygen, and which makes the bond length shorter in the phenols comparatively to ethers and alcohol. So this is the order of bond length of CO bond in the alcohol, ethers, and phenols. Okay, thank you so much. That's all for today's chemistry session. Thank you.